part of the new chapter is called implicit differentiation. So the word differentiation just means finding derivatives, right? Derivatives. Implicit. Okay, so implicit and explicit. Those are two different types of equations or functions. The ones we've been doing this whole year so far is what we call explicit. So explicit are function that can be expressed as an equation in terms of one variable. So anytime we can solve for y or x equals, or sorry, not x, f of x, solve for y or f of x equals. That's explicit, right? Those are the equations we've been doing last chapter. You guys just took a test on them. So now we're going to be looking at, in this section, what's called implicit. Implicit. These are the guys where it's very hard to solve for y. There's two y's. There's a y cubed and a y. It's hard to get y by itself if there's multiple y's, right? And we can't combine like terms. These aren't like terms. So we can't combine them. And we can't really isolate them. We can isolate x, and that's usually what we end up doing. So the equations that are x equals something, those are implicit, what we call implicit. It's difficult to express y in terms of x. What that means is it's difficult to say y equals. Okay? They're implicit. These aren't functions. If I were to graph them, they wouldn't pass the vertical line test. Okay? They are things that our calculator has a hard time graphing because they're not functions. Okay? They're implicit equations. Okay? So pretty much it's just when I can't get y by itself, what do I do? Here, I can get y by itself. It's already by itself, right? There's only one y, get it by itself. Implicit, I can't do that. Okay? So that's the difference. So today we're going to look at only these guys. We spent a whole chapter looking at these guys. Now we're going to have this section, just this section. We'll come back to explicit. We'll come back to explicit in the chapter. But for today, we're doing just implicit. How do we find derivatives of these guys? Okay, so let's start with some basics. So even though they're implicit, we still use the same rules. The last test you guys took, the one you guys took on Monday and yesterday, was called rules for differentiation, right? Because you used the rules. You used product rule, quotient rule, chain rule, those rules, right? You still use those same rules. We're still using it. I'm not teaching you any new rules. Those are still the rules we're going to use. But they need some modifications. There has to be some modifications. Okay? So what exactly does this guy mean? We've seen this guy. You guys have seen this guy almost every day in this class, whether it's on notes, whether it's on an assignment, a practice assignment, whether it's on a quiz, whether it's on a test. You guys have seen this guy every day. It means derivative, right? It's another way of saying f prime of x or y prime, right? But what does the d mean? What does the y mean? Why is there division? What does it exactly mean? So this is what it means. So when we do this, it means the derivative of x with respect to y. The derivative of x with respect to y. So when we're finding derivatives, that's what we do. We find the derivative of all the x's, and we set it equal to y. Just like the second one, right? When we found the derivative of y equals 3x squared minus x plus 2, what you're doing is you're saying the derivative of y with respect to x, is 6x minus 1, right? How do I do that for this guy down here, though? What I'm going to be looking at is guys like this. How do I find derivatives with guys like that? Well, what's the difference between the one I found? Let me highlight that in orange. What's the difference between the guy in orange and the guy in green? It's got y's, right? It's got y's. Multiple y's. I can't solve for y. I can solve for x. I can't solve for y. So the green is considered implicit. The orange is explicit. So we're still going to use the same rules. I use the power rule, right? I use the power rule to come up with 6x minus 1. I'm still going to use the power rule to find derivatives of this. It's just going to look a little bit different than what you're used to. Okay, let's see. Do I do it later? No. So this is how we do it. I'm going to show you how to do it. So anytime there's an x, x is, so we always find derivatives of x. X, how do I say this? It's an x-based world. Y's just kind of live in that world, right? So when we find derivative of x, so x squared, you do the same thing. 2x. But when we're, let me change the colors here so I go term by term. So we found derivative of that one. Now I'm going to find the derivative of this guy. Doesn't have an x, it has a y. But guess what? I'm going to use the same rules I just used before. So I'm going to use the power rule for the yellow. So if I use the power rule, what would I get? Negative 6y squared, right? Yeah, you're right. That's it. Here's the one caveat. Here's the one modification. Anytime you're finding derivative of y, you have to give it a tag, a dy dx tag, because it's not x. So you have to give it a tag. It's technically multiplication, but you don't have to put the dot there. So when you're finding derivatives of y, put the tag in there. Okay, next one. Let's see, derivative of positive 4y. What do you think the derivative of positive 4y would be? Positive 4, you're right, positive 4. But since it was a y, we have to include a tag, dy over dx. Equals. And then we have 2 at the end. What's the derivative? 2 doesn't have an x or a y. So what do you think the derivative of 2 would be? 0. Just like last. So anything that doesn't have a y, do like you did last chapter. Anything you did that doesn't have a y, do what you did last chapter. Or anything that has a y, that's where it's going to change. We got to give it a little tag. That's the first change. That's the first modification. The second modification is I have to solve for that tag. So at the end, I want to say dy over dx equals. I have to get those little tags isolated. Okay? So to do that, it's going to take not calculus, it's going to take a little algebra to get something by itself, right? To get something by itself, we just use algebra. So the first thing I'm going to do is I'm going to subtract 2x from both sides. So I have negative 6y squared dy dx. plus 4 dy dx equals negative 2x. So my goal is to get the dy dx's by themselves. Nothing, I don't want the negative 6y squared. I don't want the positive 4. I don't want those. I want those over here. So how am I going to get those by themselves? Divide, yeah. Actually, factor, which is division, right? I have two terms. I have this guy, and I have this guy. What do they have in common? Dy dx. Can I factor out a dy dx, which is division? So when I factor out a dy dx, that leaves just negative 6y squared plus 4. You guys have done that before. That's just the GCF. I'm just factoring out GCF. Now it's multiplication, right? Now it's dy dx times negative 6y squared plus 4. How do I get dy dx alone? Isolated. So what is the dy dx on the outside doing with the parentheses? Adding, subtracting, multiplying, or dividing? Multiplying. What's the opposite of multiplication? So divide by the stuff that I don't want to stay. Anything divided by itself just makes a 1. The only added step that I would do is that all of these guys can be divided by 2. All of these guys here can be divided by 2. So divide them all by 2. So you get negative 1x over negative 3y squared plus 2 to reduce it. And you're done. That's the derivative. That's how we find derivatives of things that have y's with x's. Okay? So that little caveat is what we're going to do. Anytime you're finding derivatives of anything with a y, give it that little tag, and then isolate that tag. Get that tag by itself. Once you do that, you're done. You're still using power rule. You're still using quotient rule. You're still using product rule. Okay? All right, so let's look at the first technical example that we're going to do. The first example. So I put a lot of problems in there. We might not do all of them. I just always put more than maybe you'll need, just because if we need some extra practice, if we don't, we won't do them. So there's a lot of problems in there, but will we do them all? Probably not. Okay, I just want to do enough so that you understand it. I wanted to give you different things, different looks. Okay, example number 1. If 3y squared equals x squared plus 2x to the third minus y to the third, find dy dx. Okay, that means find the derivative, right? This is implicit because I have y's and x's living together. When I have that, it's implicit. So I'm going to do piece by piece. I have 4 things that I need to find the derivative of. First thing is the pink. 3y squared. So how do you think I'm going to find derivative? What is the derivative of 3y squared? 6y. But I found a derivative of y, right? So I have to give it that tag, dy over dx. Anytime I find derivative of y, I want to give it that tag. The next one was the yellow. What's the derivative of the yellow? 2x. It's just an x, so I don't need to give it the tag. 2x, just like we did last chapter. Orange. Again, another x, right? Positive 6x. Squared. Last thing is the blue. Negative 3y squared, but it's a y, so I have to give it a tag. dy over dx. That's the first step. Step 1 is done. Step 2, get dy and dx by itself. Okay. So let me use a different color that I haven't used. These two guys have a dy dx, right? So anything with a dy dx, I want to get them on the same side of the equal sign. One is on the left side of the equal sign, one is on the right. So I want to get them on the same side. So what I'm going to do is I'm going to add 3y squared dy dx to both sides. That'll remove it from that side and bring it to the other side. Six y dy dx plus 3y squared dy dx equals 2x plus 6x squared. So now everything with a dy dx is on the left side of the equal sign. Everything on the right does not have a dy dx. Do the same thing we did. How did we isolate dy dx in the last problem? Factored it, right? So I'm going to factor dy dx out. That leaves 6y plus 3y squared. Last step. How do I get dy dx by itself? Divide. Divide by the stuff I don't want. So I get dy over dx equals 2x plus 6x squared over 6y plus 3y squared. The last guy. Can I divide everything? No, because of that 3 at the end, right? Because of this 3 at the end, 2 doesn't go in there evenly, so I'm done. That is the derivative. So essentially, you're doing the same thing you've been doing, just with a little modification. Anytime you find derivative of anything y, dy dx. And then set them equal to each other. Or sorry, isolate the dy dx. All right. Okay, so do number 2 now. Try number 2. We've done 2 examples. Let's see if you can do number 2. All right, so I found the derivative of each of them. Anything with a y, I gave a dy dx. So there's 3 terms that have dy dx's. One of them doesn't. The derivative of 5x squared was just 10x. So what I need to do now, everything with a dy dx, I need to get on one side. Everything without a dy dx, I need to get on the other side. So this guy, I need to get over here. This guy, I need to get over here. Okay, so to do that, I'm just going to do the opposite. 10x is going to be minus 10x from both sides. Negative 9y squared is just going to be positive 9y squared. So I'm going to subtract 10x from both sides. And I'm going to add 9y squared with its tag to both sides. Okay. Those go away. So I have negative 6y dy dx minus 1 dy dx plus the new guy, 9y squared dy dx equals negative 10x. Okay, so now I got to get dy dx by itself. Factor it out. Divide. So we get dy dx equals negative 10x, negative 6y minus 1. Done. Okay. All right. Okay, so let's look at number 3 now on the next page. Number 3. So number 3 actually has a slight difference between the ones we've been doing and the ones we have. It looks very similar. It's got x and y's, powers, and all that good stuff. But what's the one difference? It's equal to 0. What else? They're connected, right? We've never had that before where an x and a y were connected by multiplication. We've always had them connected by addition or subtraction, right? So that's the new thing. Okay, so let's go step by step. Step by step. So the first term is this guy in green. The second term is this guy in orange. The next term is yellow. Then this guy, and then 0 is the last term. Right. So I'm going to go step by step. I need to find derivative of every single color. Some are going to be easier than others. Okay, so the green is negative x times y squared. How do you think I'm going to find the derivative of that guy? Product rule, yeah. The green, I'm going to have to use product rule because it's multiplication. Okay? So here we go. The product rule says the first times the derivative of the second. Well, derivative of y squared, 2y, but then it also needs a dy dx because I found the derivative of y. Plus the second times the derivative of the first. Well, the derivative of the first is just negative 1. Okay, that's the derivative of the green. Orange now. 1x, the derivative of 1x, just 1. The derivative of the yellow, oh, sorry, the orange. Oh, sorry, no, we just did the orange. The yellow, the derivative of the yellow, 0, right? Derivative of the blue, negative 3y squared dy over dx, because it was a y. Derivative of the pink is just 0. Okay, so I'm going to kind of clean this up a little bit. Just rewrite it. So I have negative x times 2y. I'm actually going to move the negative 2. I'm going to write it like this. Negative 2xy dy dx. Because it's all multiplication. It's negative x times 2 times y, so I just rearrange the order. This guy becomes negative y squared because it's negative 1 times y squared. Plus 1. The 0, just you don't have to write the 0 anymore because it's just 0. And then the last term is like that. Okay. All right. So now, anything with a dy dx, I want to stay on this side. Anything without a dy dx, I want to move to the other side. So I'm going to add y squared to both sides. That one doesn't have a dy dx. I'm going to subtract 1 from both sides. That one doesn't have a dy dx. Okay. So now on the left side of the equal sign, those are the things that have dy dx's. On the right of the equal sign, no dy dx's. Factor out a dy dx. Negative 2xy minus 3y squared equals y squared minus 1. Last step. Divide by this stuff. So I get dy over dx equals y squared minus 1. On bottom, I get negative 2xy minus 3y squared. Done. It looks a lot harder than it is. It's not that bad considering you guys have done a whole chapter on how to find a derivative. The only new thing is anything with a y, give it a dy dx. And then solve for dy dx afterwards. Okay? All right, so I want you to do number 4 now. Try number 4 on your own. Number 4 is very similar. Okay, so I found the derivative. Everything that anytime you find the derivative of a y, give it a dy dx. So I did that twice. I did that when I found the derivative of negative 3y, and I did it when I found the derivative of xy. Last step, get dy dx by itself. Divide by negative 3 plus x. dy over dx equals 3x squared minus y over negative 3 plus x. Okay. All right. Okay, so now we'll probably have time to do a couple more, and then the rest we'll finish tomorrow. So let's look at number 5, example number 5. So now we throw in a cosine. We throw in a trig function. Rules don't change. Rules don't change. You guys had one on your test that had cosine of something. I think it was on the free, multiple choice part. It was cosine of something, right? What did you do to solve it then? What did you use to solve that one? If it's cosine of something, what do we use? Chain rule. We're going to use the chain rule again too. So it has 2 parts. First part, is the outside, then the inside. So we find the derivative of the outside first. The derivative of cosine, negative sign. Inside stuff stays, chain. Now you find the derivative of the outside. The inside. The 2xy. Use the product rule, just like we just did. Product rule says the derivative of the first, the first times the derivative of the second. So that would be 1 dy dx. Wait. Should be times. And then the second times the derivative of the first. Okay, so let me clean it up a little bit. Negative sine 2xy times. So on the outside, that's what I have. On the inside, I have two terms. I have 2x dy dx plus 2y. How do I get dy dx by itself? What did I figure why? Let's see. Oh, on the other side. Yeah, sorry, there is another side. So it would be 1 dy dx, which is just dy dx. So one of them's already, but I have another one stuck over here. So how do I get mathematically correct? How do I get this guy over here with this guy? I have to do it mathematically correct. I can't just divide or add or subtract or multiply. I have to do it in a way that's mathematically correct. So I have this guy times this guy. So I could divide this guy here, the brackets, but that wouldn't isolate it because that would still be on this side. This is what I say. The easiest way I think to do it is to use distributive property. Distribute what's on the outside with what's on the inside. So we get negative sine 2xy times 2x dy dx. Plus negative sine 2xy times 2y. So now I have two terms. This guy right here. On this side of the equation, I should say. Only one of them has a dy dx. So how do I get this guy over here? Add it. Because it's negative, I got to add it. So what I'm doing here has nothing to do with calculus. That's the funny thing. It's not calculus. This is algebra. You're trying to get something by itself, isolate something. So I get negative sine of 2xy times 2y equals a single dy dx plus so now I have my dy dx is on the right. This guy is just a single solitary dy dx. And then I have a dy dx tagged onto this guy. Factor it out. So when I factor it out, what's that going to leave? A 1, yeah. It's going to leave a 1 here, and then over here, everything that does not have a dy dx. Divide by what I don't need. So I get dy dx by itself. And that's it. Okay. All right. We'll save the rest for tomorrow. We might finish tomorrow.